5.3, solving trigonometric equations. So first, instead of actually solving cosine x equals 1/2, I just want you to consider it. So this is the part where you put your pencil down and you just kind of think, and we are going to graph y equals cosine x and y equals 1/2. So cosine x would be the left-hand side of the equation, y equals 1/2 would be the right-hand side. So if we're looking for cosine x equals 1/2, those are going to be the points of intersection. So our solutions are going to equal points of intersection. And again, this isn't anything you're writing down, you're just kind of thinking and listening. So I'm going to go ahead and graph cosine x. Remember that our period is 2 pi. And it goes up, middle, down, middle, up. So that goes from 0 to 2 pi. So we'll go ahead and make a scale here. My amplitude's 1. Let's fix that. It's a little bit messy. Amplitude is 1. Still messy. So here's 1, here's -1. Let's see, we know we need to label by halves of pi. So pi over 2, pi, 3 pi over 2, 2 pi. I think I will label probably 2 periods on here is enough to see what we're doing. So let's see, up, middle, down, middle, up. So here's my cosine graph. Cosine x. So now if I'm going to graph y equals 1/2, that's going to be a horizontal line. So the interesting part is now we can see really clearly there's tons of solutions here. There'd be a solution right here. It's not really at pi over 2. I know it looks kind of like it, but that's actually where my line crosses. I've got one here, here, here. So because of the way sine functions work, because it's going to keep going up and down and up and down, I am going to have infinitely many solutions. So that's the first thing that I need you to see from this graph. So again, you're not graphing this, you're just kind of thinking about it. So I need you to understand there's infinitely many solutions. And then the other thing that I need you to understand is whatever solution I have here, this solution over here is in that same, like as my function of the cosine first starts down. This one over here is kind of in the same spot on that function. This is going to be 2 pi after that first one. And then if I add 2 more pi, I would get one right over here. So that solution is going to be repeated every 2 pi. So that's the other thing I need to get you to get from this. So the first important key is just that you understand why there's many solutions, and that's because of the cyclical nature of a cosine graph. The second thing that I need you to understand is that if I have a solution on here where it crosses 2 pi later, it's going to cross again in that same spot because the period is 2 pi. So now we're going to really draw a picture to solve cosine x equals 1/2. And by picture, I mean triangles. So the 1 is my x side, 2 is my r side. So I would have to draw a triangle, and I need to make this where my cosine would be positive. So when we do inverse, we only have one triangle, but this is different because we're solving for x. So they didn't tell us, hey, do the cosine inverse of 1/2. They're saying if you do the cosine of this angle, you will get 1/2. So it's a really different thing. So I could have a triangle in quadrant 1. My cosine would be positive over here because x is a positive 1 and my r side is 2. And this side would actually be square root of 3. Let's see, square root of 3 would be across from that 60-degree angle, which is pi over 3. The other place that my cosine would be positive would be in quadrant 4, because I'm still moving over 1 to the right from the origin. And these are really ugly triangles, but it'll work. And then that angle, if I start in standard position at that 0 and go around and stop, if this is pi over 3 here, All the way around would be 6 pi over 3 because 2 pi is a full revolution. And so this angle would be 5 pi over 3. And so my solutions for x are going to be pi over 3 and 5 pi over 3. But remember, every time I go 2 pi units on my graph, and to make that connection to the circle, it's like saying if I go all the way around and stop at this angle again, because I know I can keep doing these revolutions, and as long as I land on this terminal ray, I will have another solution. So we have plus 2n pi, or n times 2 pi. Maybe it's easier to think of it as n times. So let's write it that way. N times 2 pi, and we'll have 5 pi over 3 plus n times 2 pi. So 2 pi comes from, the period is 2 pi. And so every 2 pi will have that same, we'll have a solution. So connecting this with our graph up here, this would be like my pi over 3. This would be my pi over 3 plus 2 pi. This one would be 5 pi over 3. This would be 5 pi over 3 plus 2 pi. So the reason we're using that n is because we could add 2 pi, or we could add 4 pi, or we could add 6 pi, or we could add 8 pi. We can add multiples of 2 pi, and we know that the way this cyclical sine function is going to work, I'm just going to keep getting more and more solutions as I do those revolutions. So we drew that cosine graph. Normally we wouldn't really do that. We didn't really find our answer off that anyway, but it's just to give you this idea that we have many solutions and that they repeat every 2 pi. That's what I needed you to get from that. Most of the work we're going to be doing is going to look like this triangle stuff at the bottom here. This is what we're going to be doing today. So here's a problem we're actually going to try solving, or you're actually going to try solving. So go ahead and write down example 1. And you'll notice that we have a cosine x there. So I want to isolate cosine x. Since it's on both sides, I'm just going to subtract 3 cosine x. And I know I don't need to show this step, but sometimes when we do something new, it's nice to see all the work and figure out what's going on. So now I would have 2 cosine x equals square root of 3. And then I would divide by 2. So cosine x equals square root of 3 over 2. So we're going to solve by just drawing triangles on our coordinate plane here. So my square root of 3 would be the x side, and the 2 would be the r side. And the other thing I need to think about here is I always want to look at the period and be thinking about the period. And this is just cosine x, so the period is 2 pi. And so there are going to be 2 answers. So this is similar to the one that we just looked at. In fact, it's very similar because cosine positive, we know will be in quadrant 1 or 4 again. That's wherever my x is positive. So wherever the cosine is positive is where x is positive. And this time the x side is square root of 3. We have right angles again. The r side is 2, so my y side is 1 and negative 1. I don't think we made a negative on the last one, and that was definitely an oversight. So across from the 1 would be my smallest angle, which would be 30 degrees, so that's pi over 6. And then if I go all the way around, this would be my other angle. So remember, a full revolution is 2 pi, which would be 12 pi over 6. And then I'm subtracting that pi over 6 inside. And so that second angle would be 11 pi over 6. So this is just trying to make my thinking visible about how I'm coming up with those numbers. So I have 2 angles, pi over 6 and 11 pi over 6. But remember, the way that cosine function is going to keep repeating itself, we actually have tons of solutions. So to allow for that, I'm going to write x equals pi over 6 plus multiples of 2 pi. So this time we're going to write it as 2n pi. It just looks nicer that way. If it's easier for you to write n times 2 pi, you could do it that way. And the other one would be that 11 pi over 6. And then again, plus 2n pi. And that's because every time we go around and we do a full revolution and we stop at that terminal ray again, it's really the same reference angle. We're going to get the same answer. It will still be square root of 3 over 2 when we take the cosine. So for the next one, we have something squared. So a little bit different. So we're going to isolate our tangent squared of x, and then we can take a square root, just like we would if we were solving a regular equation. So we'll add 4 on both sides. Again, just showing kind of some extra work because we're doing something new. We would divide both sides by 3. So tangent squared x equals 1/3. And then because it's squared, we have to take the square root. Remember, if I have tangent squared, sorry, let's fix that. If I have tangent squared x, that's the same thing as a tangent of x squared. This is really how we're writing it. So we need to do square root. If I square in a root, I have an absolute value of tangent x. And then when I square root 1/3, my numerator is just 1. My denominator is square root of 3. And so tangent x equals plus or minus 1 over the square root of 3. So now we have to think about tangent. So the period of tangent is only pi. So that would be one answer. But plus or minus, so 2 answers. So we'll have one positive answer from 0 to pi and one negative answer from 0 to pi. So what that period means, since the period is just pi, here's 0 here, here's pi here, that my answers are going to fall between 0 and pi. We're not going to have answers down here between pi and 2 pi. So only between 0 and pi will we look for answers. So I'm going to draw a triangle in both quadrants because I know there'll be one positive, one negative, right? So they're going to have to be in both quadrants. And both of them are going to have, let's see, tangent is y over x. So my y side will be 1. But on the right, I will have a positive square root of 3. On the left, it'll be a negative square root of 3. My radius is 2. And let's fill in these angles. So across from the 1, that's my small angle, my 30. 30 degrees is 1/6 of 180, so this is pi over 6. And then to figure out this angle, I know that all the way down to the x-axis is pi, and 1 pi is 6 pi over 6, minus the reference angle inside is just pi over 6. So this one would be 5 pi over 6. So because we are looking at tangent and it repeats itself every pi, each of these answers we could keep adding pi to and get more answers. So x will be either pi over 6 plus n times pi. And this is because the period of tangent is pi of, that's messy. Period of tangent is pi. So on the last one we had cosine and the period was 2 pi. So now this time, because it repeats itself every pi units, I just have to add multiples of pi. Or 5 pi over 6 plus n pi. So sometimes we don't want to keep writing like plus n pi, basically. We want to restrict our domain. We want to restrict what we can have for x a little bit. So now this time we have the interval from 0 to 2 pi. Remember that this means we're including 0, but we're not including 2 pi. And we're going to actually skip b just in interest of time. We did that in class as well. I just have not bothered deleting it yet. So for example 3, I really need to get everything on one side. And this is a strategy we'll use at times. So 2 sine x cosine x minus square root of 3 sine x equals 0. And then we're going to factor. So I can factor a sine x out of both terms. And then I have 2 cosine x minus square root of 3. And then we can go ahead and solve with zero product property. So either sine x will equal 0 or 2 cosine x minus square root of 3 equals 0. So this first one's already really solved. Sine x is by itself. I just have to go through and figure out what that means. The second one, I need to get cosine x by itself. And we get kind of some familiar numbers again with square root of 3 and 2. Pretty sure we already did that one. So this time for each of these trig functions for sine x equals 0, I'm going to have a couple answers. And then I'm going to also have a couple answers for cosine. So remember, cosine has a period of 2 pi. I'm going to have 2 answers. Period is 2 pi. 2 answers. Same thing for sine. I'm going to have 2 answers from that one also. Also 2 for sine. So we're still thinking about that stuff, but this time we're not going to be adding multiples. So sine of x is 0. I want to think of this as 0 over 1. Anytime I have a radius on our side that's 1, I'm thinking about how it's on the unit circle, and my y is 0. So there are only 2 places on the unit circle that can happen, and that would be here. My y is equal to 0. I didn't go up or down at all. That's my y. Same thing over here. And that would be 0 and pi. So I know that you might also be thinking that the 0 could be considered 2 pi. But remember, our interval is from 0 to 2 pi, and the 2 pi has that soft parenthesis. We're not including it. So because of that interval, we're not going to call that 2 pi. We're going to call it just 0 only. So we have 2 answers for x from the sine x equals 0. From the other one, I've got cosine x equals square root of 3 over 2. And so we'll need to draw those. Cosine is positive, again, in quadrants 1 and 4. My x side is square root of 3. My r side is 2. And then I have my y as 1 or negative 1. And then I need to fill in those angles. So this first angle across from the 1 is my small angle, which is 30 degrees. That's 1/6 of 180. 180 would be pi. So 1/6 of pi is pi over 6. And the other angle goes almost all the way around and stops pi over 6 units short of being a full revolution, which is 2 pi. 2 pi would be 12 pi over 6 minus that pi over 6 as a reference angle. So the second one is 11 pi over 6. So now I need to go ahead and list out all my answers. So from that first one, sine x equals 0, we have 0 and pi. And then from our second set of drawings for cosine x equals square root of 3 over 2, we have pi over 6 and 11 pi over 6. And so we'll make one more note. We don't add, I don't know why it's moving it. Don't add n times 2 pi because we are restricted to 0 to pi. All right, so that's just a little note about why we didn't put that in this time. And again, we knew that each of these functions, because they each had a period of 2 pi, we knew they were each going to have 2 answers. So here's another example. So we've looked at some kind of easier solving, believe it or not. Now we're going to look at what happens when you just, like on this one, I don't have just sine or just cosine like I did on those first couple. And then on the last one, I was able to factor some stuff out, and that's just not going to happen here. I've got a sine squared x, I've got a sine x. It's just not going to work the same way. So I need to remember those Pythagorean identities. So I need to remember that if I have cosine squared theta, actually sine squared theta plus cosine squared theta is going to equal 1. It doesn't really matter if I reverse that order, but this is the way that we learned it. And if I wanted to isolate cosine squared theta, I would do that by subtracting sine squared theta. So cosine squared theta equals 1 minus sine squared theta. So what I'm going to do is I'm actually going to choose to substitute for cosine squared of x. And the reason I'm substituting for cosine and not sine is that I also have this sine here that's not being squared. So if I was to replace this one, then I would still have a sine. I would have cosine, sine, and cosine. I would still have a mess. So the best way I can do this is just to replace my cosine squared x so that I have an equation that only has sine in it. So now I have sine squared x minus sine x plus 1. And instead of cosine squared x, I have 1 minus sine squared x. So I need to get everything on one side, probably do some factoring here. So we're going to subtract 1 and add sine squared x. And I don't have to show this work, but again, when we do steps like this, I find it's just helpful. So let's see, now I have 0 on the right, so I'm going to be able to factor. Sine squared plus sine squared would be 2 sine squared x. And then I have minus sine x. And then the plus 1 minus 1 is just gone. It makes a 0. So now I can factor. I can factor a sine x out of both terms. And then we're left with 2 sine x minus 1 equals 0. So now it's kind of like the last one where I have to do zero product property, either sine x equals 0 or 2 sine x minus 1 equals 0. And on the left, it's already solved, and it's even kind of familiar answers. On the right, on this part of my equation, actually I have to solve and get sine x equals 1/2. So sine x equals 0, again, this is 0 over 1. So my y side is 0 and my r side is 1. So those are just going to be spots on the unit circle. So here my y is 0, x is 1, y is 0, r is 1, and that's 0. So we're restricting this one again from 0 to 2 pi. So I'm not going to call it 2 pi. I'm just going to call it 0. And then over here, my angle would be pi. Remember, it's wherever it goes around and stops at. So it stops at pi. And on that side, let's see, my x is -1, my y is 0, and my r is 1. So I don't have to list all this stuff out. I think it's just good review for us. For sine x equals 1/2, my period of this one is also 2 pi. I'm expecting 2 answers. If my sine is positive, sine is y over r. That means I'm going to be in quadrant 1 or 2 because y is positive in both of these quadrants. So sine theta is positive because y is positive. I'm just writing that in both quadrants. Just good review, something to think about. So then I'm going to label my sides. My x or my y side is 1, my r side is 2. And then my x side is either square root of 3 or negative square root of 3. So to label our angle, across from the 1 is my 30-degree angle. 30 is 1/6 of pi. So, or 1/6 of 180. So this is pi over 6. And then this one, if I start here and I go around, all the way to the x-axis would be 6 pi over 6. But I have that reference angle of pi over 6 inside. So this would be 5 pi over 6. So that's the one that goes around and stops. So now I have 4 answers. I have x equals 0. I have x equals pi. So I've got 2 answers from this sine equation that I had to solve. Sine has a period of 2 pi. I expected 2 answers. And then when I solved the second one, sine has a period of 2 pi. I expected 2 more answers, and I got them. Pi over 6 and 5 pi over 6. But I have some bad news. We're not done with this one yet. So we need to check answers. And the reason we have to check answers on this one and not the others is that we substituted trig functions. So we are checking answers because we subbed trig functions. So because I replaced my cosine squared of x with 1 minus our sine squared of x, we have to check this. So because we sub trig functions, we do have to check our answer. We have to check it back in the very original problem. So as you can imagine, now we've got 4 answers to check. It's going to be pretty time consuming. Sometimes they all work, sometimes half of them work. You just can't be sure. We're just going to have to check. So my original, so that I can see it, was sine squared x minus sine x plus 1 equals cosine squared x. So this is the one I'm checking. And first I'm going to check x equals 0. And the good thing is I've already got the picture drawn. So I will have sine squared of 0. So remember, that's the sine of that angle 0, and then I square it, minus sine 0 plus 1 equals cosine squared of 0. So sine of 0 would be my y value at 0. So here is 0, and my y value is 0. So this is going to be 0. 0 squared is still 0, minus 0 again, plus 1. And then my cosine squared of 0 would be my x value. Cosine at 0 is x equals 1. So this would be 1 squared. And that means 1 equals 1. So our first answer checks. Now we're going to want to check pi was I think our second answer in that picture. So now we'll check sine squared pi minus sine pi plus 1 and see if that equals cosine squared pi. And if I look up cosine, okay, so sine of pi would be my y value at pi is 0. So 0 minus 0 plus 1. And my cosine at pi was my x value at pi. So that's going to be that, I can't scroll back and forth right now, but that was that negative 1. And then I square it, so I get 1 equals 1. So now I would have to check the other two. So now we'll check 5 pi over 6. And I'm going to have to redraw these because I won't be able to see them. This one doesn't even look like it could work, but we still have to check it. So to redraw those, let's see, what did we have? We had 1, 2 square root of 3. And this was our 5 pi over 6. I don't know why I'm checking 5 pi over 6 before pi over 6, but it works. Pi over 6, 5 pi over 6. So I'm kind of checking them backwards, but that's okay. So 5 pi over 6 would be from this blue triangle over here. So sine is y over r, so that's going to be 1/2. And then remember, I have to square it because it's sine squared. Minus, this is just a regular 1/2 plus 1. And my cosine squared of 5 pi over 6, so x over r would be square root of 3 over 2, negative square root of 3 over 2. And then remember, I have to square that as well because it says cosine squared. The negative 1/2 plus the 1 is 1/2. 1/2 squared is 1/4. 1 times 1 is 1, 2 times 2 is 4. On the other side, square root and square cancel. I just have 3, and now it's positive. And my denominator, 2 squared, is 4. So this one's going to check. And then the last one, I'm checking that pi over 6. I'm going to try and squeeze it in on the right. Sine squared pi over 6 minus sine pi over 6 equals cosine squared of pi over 6. So now we're working with the triangle on the right. So it's almost the same. The only difference is that square root of 3 is now positive. Everything else, my sine functions are going to have the same value. Oops, there was a plus 1 in here. So I can already tell if this is a positive because I'm squaring it, I'm going to get exactly the same value as the last time. I will get 3/4 equals 3/4. So it turned out on this one, even though we subbed like that, all of our solutions actually worked. So I know it feels like we wasted our time, but it's definitely good for you to see an example like that. So sometimes we're going to use other tricks. So on example 6, we have something, I can't sub anything. There's no way to take sine and write it in terms of cosine. So sometimes what we have to do is a trick could be to square both sides. And I want to square it so that I can use those Pythagorean identities. The problem is if I take this and square it right now, I'm going to get sine squared x, so don't write this down, minus 2 sine x cosine x plus cosine squared x equals 1. So the issue is that I could substitute for that sine squared x. I could make that into a cosine, but I still have this middle term where I have a sine and a cosine. So before I try this magic squaring both sides method, I am going to go ahead and I'm going to add cosine x on both sides. That way, when I square both sides, I do not have to worry about that middle term. So here we are going to square both sides. And this is random. This is something that you would never really know to do unless you're kind of told that there's this trick. But the reason is that we want to use Pythagorean identities. That's the really only way that we can sub sine in for cosine is if it's squared. And so we're going to make it squared. We're going to force it to be squared by squaring both sides. So on the left, when we square, we now have sine squared x. On the right, when we square, we'll now have cosine squared x plus 2 cosine x plus 1. So because I have almost everything in terms of cosine, I'm going to substitute for sine squared. So remember, and it's okay to write down these Pythagorean identities every time you use them. What's not okay is doing it wrong. So this would go over on my scratch paper. Sine squared theta plus cosine squared theta equals 1. That's that original identity. Sometimes just looking at it, you can rearrange it. If I want to solve for sine squared, I would have to subtract cosine squared on both sides. So now I have something to substitute. This is going to be 1 minus cosine squared x